Hello everyone. So today I'm going to present you our summer research for astronomy. And the title is called Finding Effective Temperature of B-type supergiant stars with Spectrophotometry. My name is Jingyu and we're from Agnes Scott College. So what we're doing is that we want to know that effective temperatures of the stars that are difficult to determine and therefore really heavily rely on the stellar atmospheric models. As astronomers know that strong stellar wind can affect atmospheric conditions of B supergiant stars and can also affect how well observations agree with our pre-existing models. So this summer, we want to focus on finding the effective temperatures of B supergiant stars with spectrophotometry method and conducting stellar atmospheric model fitting. And we test the existing model to Telesta B star 2006 and Atlas 9 model with B supergiant parameters such as the reddening, EB-E, log G, and effective temperatures. So the research question we want to ask is how much the strong stellar wind will affect the observational agreement of our atmospheric model. So on the left-hand side, you can see it's the SED plot for a star that we study. It's the log wavelength versus the log flux. And the right-hand side is a star, it's a supergiant star that we find as an image. Here is an awesome group photo that we take over the Zoom call. We did this research totally virtual, all virtual online, and because the COVID-19 circumstance, but we love our group and we are the pioneer for online research. The method we use is called spectrophotometry, and we create contour maps and SED plots. The contour maps are chi-squared contour maps, chi-square of the reddening EB-V as a function of angular size and effective temperature. The contour maps are the result of the fitting models of the SED plot, and each contour lines are the best fitting lines. And the right diamond in the middle side, you can see indicate the best fitting model temperature for our directly determined angular size. So we currently we have 4 stars have the directly observed angular size from Charo interferometer, but we're gonna have more in the fall semester. And the SED plot, the spectral energy distribution plot, tells us that the plus sign shows the collective spectral fluxes, and solid green line shows the SED derived from our interferometric size and the best fit temperature and reddening. And the dashed line is the SED derived from the temperature and angular size predicted by the model. We studied totally 20 star samples, but we only have 4 stars with the angular size observed by the interferometer. So here comes the result that we have 2 comparison plots. The left-hand side is the star temperature comparison between derived temperature, model temperature, and literature temperature. The 4 star samples can briefly tell us that the derived temperature is higher than the model predicted. And the right-hand side is the star angular size comparison between the measure size and the model size. And you can see the model size is higher than the measure size. So this actually feeds our hypothesis that our model under-predict the temperature and over-predict the size. And lastly, I'm going to show you our scatter plot. We plot for all 20 stars with UV and without UV because we think they might have a difference. That way that's why we do a difference between like the color and the shape of the square and the triangle. And the model temperature and literature temperature, we compare them by using this y equals x line. To indicate that when they're equal and the rest of them are going to be unequal. And you can see most of the dots, the plots are on the upper left of this graphs, which kind of tells us that literature temperature is higher than the model temperature. And indeed, we calculate that we find that literature temperature is 3.65% higher than the model temperature. And in the future, we're going to include more samples here. Thank you so much for listening, and thanks for the funding from the Francis Marx Shalom Women in Science Fund and Anonymous Alumni 1964 Research Fund. Thank you for listening.